Hello everyone. Let's continue talking about regression. Previously, we introduced linear regression and the Bayesian solution for regression, and we introduced nonlinear regression, so it's time to talk about the Bayesian solution in the nonlinear case. And specifically, we'll introduce kernelization and Gaussian processes. Thus far, we have established that nonlinear regression is very similar to the linear regression model, but we just pass our inputs x through a set of nonlinear functions. Everything else falls into place by just replacing x's with z's. But we found that if we do that, we're going to have the same confidence in places where we don't have much training data as we have where there's lots of training data. And that's where we need a Bayesian formulation on nonlinear regression. And that takes us to Gaussian process regression. So if we work out the formula for the distribution when we're making a prediction of W star given our input data X star passed through the nonlinearities, we'll get this slightly intimidating looking equation. So it's a normal distribution with a pretty complicated mean and covariance. But we can remind ourselves of what it looked like before when we did the same Bayesian predictive density in the linear case. And actually, you see, it's very similar, except the x's have all turned into z's. So we already know how to achieve that. And when we plot the learned model, it looks something like this. You can start off by looking in subpanel B, where you see each of the basis functions has been weighted, sometimes positively, sometimes negatively. And they all contribute so that when we sample from our model in the Bayesian form, we can do that, and we can talk about different models and how all of them have non-zero probability. Those can then be used as weights to combine to make our posterior distribution on W as a function of the inputs x. So we've integrated out our model parameters, and we've also we're not showing here the nonlinearities, because the nonlinearities, the z's, are just a means to an end. Now, we could just stop there, but actually the kernel trick is going to help us with some inefficiencies, and actually it will free us up in some interesting ways. So if we look at that predictive density equation again, so back to using z's for to do our nonlinearities, we'll see that what's happening is kind of a two-step process. We take our input x, turn it into a nonlinear response z, and then we look at pairs, in fact, of z's, where every time you see a z, it's either a vector and a matrix, so a single z star, so that's what we're trying to predict, and our data set of z's, or it's a matrix and a matrix multiplication. We're taking these products of z's after we've created a nonlinearity. But actually, the kernel trick says, well, what if we could do both of those steps simultaneously? So we'll take the data, two data points, xi and xj, and we'll return directly the value of doing that dot product between them. So measuring, in essence, the similarity between xi and xj. It's what we'll need eventually for the Bayesian formulation anyway, but what if we could do these two things in one step? And in fact, the kernel trick is about never computing z explicitly. You might say, well, z is a known function, what's the problem? But actually, if you want to have a very high dimensional z, you might find that it's very, very expensive and prohibitively so. And in fact, when we introduce now the kernel trick, you'll see that there's actually a massive opportunity here in terms of maybe simulating an infinite dimensional f of x in some special cases. So we have here Gaussian process regression. It's Gaussian. This part of the Gaussian process regression refers to the fact that we have a normal distribution for our predictive density. When we were dealing with the nonlinear model, where we were explicitly creating the z vectors, you see the top half of the slide, but we could replace each instance of this z multiplication with itself using a kernel function. So a kernel function, for now we could just treat it as some sort of function that either takes a vector and a matrix as an input, or it takes a matrix and a matrix as an input. It captures the process of making dot products and measuring the similarity between inputs xi and xj. So each element of that matrix can be computed individually this way with a k function. Now, you should be asking, right, well, what k functions can I use? Is it up to me? What choices do I have? We have a lot of choices for the kernel. So we can have a linear kernel where we measure the similarity between xi and xj by doing this dot product. You can have degree p polynomials. You can have radial basis functions. Here, for example, is pictured a Gaussian, which looks at the similarity between xi and xj. And I would note that these are all kernels inside of a Gaussian process regression. The idea is that what we do here affects the mean and the covariance of a normal distribution on W. And of course, it's looking at the similarity between the x's after we've passed them through some kind of nonlinear function. So you can have Gaussian process regression with a nonlinear kernel, or you can have Gaussian process regression that uses a Gaussian kernel. So let's keep track of those two parameters that we can choose. The other neat thing to note here is that when you have a radial basis function, Gaussian or not, you could think of it as using an infinite dimensional f of x, as in a set of basis function z. And you think, how is that possible? Previously, when we used radial basis functions, we used a Gaussian and we shifted it by translating it with different alphas, alphas 1, alpha 2, alpha 3, and we said we could have 5 or 7 of them. They would respond differently to different inputs x. Well, when we were doing that, we were basically saying that there is a strong response near for data points that are near that offset Gaussian, so near that alpha. When x was similar to alpha, there would be a strong response. And then far away from it, you would have a very quickly falling off response because Gaussians drop rapidly. That meant that for most of the number line, for most of the response of that dimension of z, you wouldn't have a very strong activation at all for a given data point xi. And that's basically what's happening here. We're looking at every combination of xi and xj, and we're saying that there's a strong response near those two data points and how they interact, but everywhere else there's practically a zero response. And how much interpolation happens is dictated here by lambda squared. We see here 3 different RBF kernels based on different values of lambda. In the first one, figure A, sub A, we have a large lambda, and so we see that the function that results is actually quite smooth. It doesn't try very hard to go through all of the training data. The middle one has a small lambda, and so it's not doing very much interpolation between the data. It's trying to stay faithful to it, and so you can see that the model now goes through all the data points as much as it can, but then ends up being quite uncertain and washed out in any places away from the data. It's interesting that you can get a lambda that actually does a pretty good balancing job between fitting the data, but also trying to interpolate in areas of low data. And this is a job for a maximum likelihood learning of the length scale. And so again, this is something that can be optimized using actually a nonlinear optimization. Similarly, for the variance, we've just been working on the assumption that we have a fixed variance, and we've just been optimizing our means. But we could do an optimization that's going to be a nonlinear optimization to find our maximum likelihood values of sigma. And That's a process that we'll talk about more when we get into nonlinear optimization later in the term. Now we've established how to do linear regression and the Bayesian form, nonlinear regression and the Bayesian form of that. It's time to move on to sparse linear regression. Sparse linear regression comes into play when we think that we have dimensions in our data vector x that may not be helping. We'll address this problem by imposing a prior on our model parameters. Imagine that not every dimension of x is informative. We've measured things about the real world and coded them in a long vector, but just to be sure, we've encoded more things in that data vector than we strictly needed. Now our model is having to learn parameters for each of those dimensions, and potentially it doesn't have enough interesting data to make that worthwhile and to realize that that dimension really isn't informative. We can try to address this by introducing a sparseness prior that's basically going to emphasize and say the model is allowed to have a number of non-zero weights in the phi vector. So some of the dimensions of x are going to be important, but you've got a limited budget, and so you've got to choose which of the dimensions of x we're going to emphasize, and we're going to set the rest either to 0 or very low. We're going to achieve this by introducing a product of t distributions. So imagine a t distribution, student t distribution, which has long tails, but we're going to multiply one along one dimension and another along another dimension, so we have a figure like the one shown here. In other words, in our joint space of weights that we could apply to dimension 1 on the horizontal axis and dimension 2 on the vertical axis, we're saying that combinations where the two weights are close to 0 are possible and have a high probability. Possibilities or scenarios where one of the dimensions has a non-zero weight are all quite possible, but combinations where both elements for the first and second dimension of a data vector x have some high weight, high positive or high negative, these are very low probability and should be de-emphasized. So how do we make this prior to life? Well, we said we can represent this as a student t distribution, and we know that the student t is a product of gamma functions. And so here we have d for the number of dimensions. In the figure previously, we had 2 dimensions, and everything else about this function should be known. Basically, we have a fixed gamma function in MATLAB, and we have a zero mean, simple covariance, and we get to set the new parameter, new right there. So we come back to our Bayesian formulation for learning of our model parameters, except now we don't have a conjugate prior. This element probability of phi is based on this student t distribution product that we just established, and so we're going to have to be a little clever about that. We can rewrite that prior as a product of gamma functions, and so you'll notice here that now we have this integral where we're integrating out our hidden variable, and we've got the product over the multiple student t distributions, one for each dimension. The hidden data, the hidden variable rather, is going to be this H matrix where it has diagonal entries, everything else is 0, and because it's h to the minus 1, you've got basically 1 over h sub d for each of the d dimensions inside of h. This will be important later because we're going to be estimating h sub d's, and I'm just pointing out that the matrix actually has these inverted. So we've got that prior for our model, and that represents this part of our equation when we come to do inference. When we're doing inference, we're looking at our model prior, and we're looking at our likelihood term here, which is a normal distribution on W given our parameters. Now, when we multiply the normal times the normal, we can rewrite that as a new normal distribution on W, and we still have our product of gammas as the second component. We still can't conveniently solve for our model parameters here by through a closed form. But there is an approximation that we can get where we're going to find that the h parameters that we need, we can choose them by maximizing this equation here at the bottom. It is still a product of gammas, and it is multiplied by a normal distribution. And we can do that through an EM process. So expectation maximization, where we're going to alternate by fitting the h parameters iteratively while fixing our model parameters, and then switching and updating our variance based on fixed h parameters. We're going to step back and forth until convergence using expectation maximization. We have all the equations so we know what the A matrix is, and we can compute our covariance. So this process should be fairly simple to implement. But I'll point out one thing here. So let's take the case where we've converged, and now we find that our h sub d is a large number. So if that's a large number, we said that our capital H matrix is going to be full of 1 over h sub d. So for each of the dimensions, it has an entry along the diagonal, which means that a large h results in small values in 1 over h. And that means that that dth dimension, that particular dimension of the x vector, is going to be de-emphasized. So a high h has encouraged our model to ignore that dimension of the x vector. It's saying that measurement from the real world isn't very important in determining the probability of W. We can picture the result of doing regular linear regression on the left or doing the sparse version on the right. And now here we just have 2 dimensions in our x, so that's our x1 on the horizontal, x2 on the vertical. And we have our training examples pictured here as blue circles. Now each blue circle has inside of it a fixed color of heat, I guess. You could think of the white as being white hot and the black here as being dark and 0. And so we're trying to fit our model to explain all of these different blue circles, and either with the traditional way on the left or using our sparse prior on the right. Now you notice on the left that there's a slight slant, so these sort of equiprobable lines are all angled, and on the right, now they're all completely vertical. We've established on the right basically that the x2 dimension isn't adding a lot of information. It's true that the log likelihood is better on the left. We've done a better job of explaining the data, but if we think that our model might be might have too many degrees of freedom and it needs to be simplified, then the model on the right does as good a job as possible while de-emphasizing one of the dimensions of the x vector, x2 in this case. Now, this is effective, but there is a problem with this. We've had to introduce one hidden variable per dimension. So if we have a really high dimensional input vector x, this might actually be very complicated, very costly to solve for. And remember, we're doing EM, so we're going to have to solve for it repeatedly and iterate. This is where we'll introduce the dual model next time.